So today, what we're talking about is classifying numbers. And this process of being able to classify numbers is really important because it helps us to be able to accomplish the standards we have, and I've got those listed on the screen in front of you. A part of doing those standards to identify, interpret and justify those appropriate qualities for modeling, you got to understand how to classify numbers to do that, as well as that second standard there, where we want it to represent the constraints on equations or inequalities. And primarily for the first part of this, we're just strictly limiting ourselves to those two parts. Later on, we'll be working with the other parts of that standard. So classifying numbers, you may have seen some of this before or not, but when we classify numbers, we're going to start out with the very basic number that we ever had. And you may recall when you were in like preschool, they taught you to count, didn't they? Well, what we did is we taught you what we call natural numbers. Natural numbers, we call them natural numbers, I guess, because they kind of occur naturally. If I were to count everybody in this room, I wouldn't start out by counting, 0. Now, 1, 2, 3, 4, 5, would I? Does anybody count that way? You go to count the number of cars in your driveway. You don't go 0, 1, 2, 3. You don't start out with 0. You start out with what? 1, absolutely. So natural numbers start with 1. So what I would want you to write down is, first of all, natural numbers. They include 1, 2, 3, 4. And the symbol for natural numbers is a kind of a fancy N with a double line on the diagonal. Anytime I refer to natural numbers and I just want to write a notation for that, I would put that symbol N, meaning natural numbers. You might also want to include that natural numbers do not include 0. It does not include negatives. It does not include decimals. It does not include fractions. In fact, all it is just the natural numbers, 1, 2, 3, 4, 5, and so on forever. That's the basic number that we would ever talk about. And then when you get to kindergarten, we introduce you to whole numbers. Well, the thing about whole numbers is whole numbers are really natural numbers with one other number, that being 0, because 0 means there's nothing there. But 0 is considered to be a whole number. It's important to understand 0 is in of itself a number. It tells us that, if you had $3 and you go to the store and you spend $3, you now have $0. The best way I can remember this is that whole numbers, which will include the symbol W to represent whole numbers, if that's what we mean. It also includes 0, but there are no negatives, no decimals, no fractions. And I like this word written this way, the word whole with a capitalized O, meaning whole numbers just include 0 in addition to the natural numbers. So we go on to middle school from elementary school, and they teach you about something called integers. Well, integers are a whole lot like the natural numbers and the whole numbers, but they also include negative numbers. We introduced to you in middle school for the first time a negative concept. Negative can be lots of things. You can look at elevators as positive and negative. You look at ocean. We talk about sea level and below sea level as being positive and negative. Sadly, the thing I'm most familiar with is that money deposited in the bank I tend to have more negative money, seems like. I'm not sure why. I'm sure something about my children have something to do with that. Remember, natural numbers, we gave an N. Whole numbers, we gave a W for a symbol. But for integers, we use the symbol Z. Now, integers includes 0. It includes all the positive whole numbers and natural numbers. And now it also includes negatives, but it does not include, integers does not include decimals or fractions. There are never any pieces, parts of integers. Integers are, not mathematically correct to say it, but it's really kind of like positive and negative whole numbers. You graduate to high school, we start beginning to realize that there's a bigger number system than that. There's rational numbers. Now, rational numbers are the natural numbers, the whole numbers, the integers, both positive and negative. For rational numbers, will represent rationals with a symbol of Q, integers Z, rationals Q. I definitely want to write that down because that's kind of hard to remember. It definitely includes 0 and negatives, and now rational numbers include decimals if they repeat, such as 2.33333 forever and ever and ever, or if that decimal terminates like 1.25. It includes normal fractions. I'm not exactly sure what we really mean by normal fractions, but anything that can be written as a fraction is a rational number. All rational numbers can be written as a fraction. Now notice in the chart here, we've got some things that are non-examples. Rationals are not decimals that repeat, decimals that go on that never repeat. Rationals are never decimals that go on that never repeat. Rationals are not negative square roots. You can't have a negative square root. It's not a rational number. In fact, we would call that an imaginary number. And we'll talk about that a little bit more here in just a minute. And finally, pi, 3.1415, on, it goes on forever and ever. That is not a rational number. It's an irrational number because that decimal never repeats. A few more examples of rational numbers here. This is 0.1253535353. That's a repeating decimal, so it's rational. Or 1.752, 752, 752, 752. That's a repeating decimal. It goes on forever and ever, and it repeats. That's a rational number. Or 2.333333. All these are rational numbers. They're decimals. They terminate. 1/4 is 0.25, or 1/5 is 0.2. 1/2, 0.5. 1/8, 0.125, or 1/10, 0.1. If the decimal terminates or repeats, it's a rational number. It's when it never repeats and goes on forever and ever that it's an irrational number. Any of the fractions are rational numbers by definition. Now, we talked about natural numbers, whole numbers, integers, rationals, and reals. We've talked about an irrational number is one that goes on forever. Pi is an example. Any number that never stops. In fact, any square root that does not have a perfect square number under the sign is an irrational number. For example, think about what I mean by that. We all probably know that the square root of 4 is what? 2, yeah, right? Because 2 times 2 is 4. In fact, the square root sign means the principal square root. But we also know that the square root of 4 could also be -2 because -2 times -2 is +4.
I learned a little bit of this.
Oh yeah, you should have. That's cool. Well, let's kind of summarize the radicals, just so you know, because square root and the word radical basically means the same thing. Now think about it for a minute. The perfect square roots are the square root of 1, the square root of 4, the square root of 9, square root of 16, the square root of 25. And think about, though, how I got that. That's 1 times 1, and that's 2 times 2. That's 3 times 3. That's 4 times 4. That's 5 times 5, right? But notice what's between. Between the square root of 1 and the square root of 4 is the square root of 2 and the square root of 3. Correct? Yeah, these, if you put those in a calculator, let me just take my handy dandy cell phone calculator here. And let me put in my cell phone calculator so you can see it. Let's figure out, what is the square root of 3? Whoa. The decimal doesn't repeat. Goes on kind of forever and ever. So what I realized about that, the square root of 3 is irrational. In fact, every radical between the perfect squares will be irrational. So that means the square root of 5, square root of 6, square root of 7, square root of 8. Those are all irrational. Square root of 10, 11, 12, 13, 14, 15. Those are all irrational. Only these, square root of 1, square root of 4, square root of 9, they have perfect square roots. Those are the only ones that are rational. All the others are irrational. Okay? So that helps us when we classify numbers. Now, you noticed on one of the slides a minute ago that we said we had, we're going to kind of mention, and I'm not sure we've actually seen it yet. We get here. Something called real numbers. If in math we have real numbers, then it means also we have something else. What's the opposite of a real number? What do you think? Okay, if I told you that I don't want to break your hearts here, but Santa Claus was not real, what would you say he is? He's what? Somebody's crying online now. They didn't know that. No, I was kidding. What is he? He's Man, thank you. Okay, imaginary. Actually, if you still believe in Santa Claus, he is real, so just ignore me saying it. Imaginary. Okay, so here's what we've got. We have real numbers, and we have imaginary numbers. And you're like, dude, what could an imaginary number be? Aren't they all real? Well, we will not talk a lot about imaginary numbers in Algebra 1. We deal mostly with real numbers in Algebra 1, but we will deal with imaginary numbers quite a good bit in Algebra 2. But just so you know what an imaginary number is, think with me just for a second. Back to our square roots. we said the answer to this was 1 and this was 2, right?
Teachers, please pardon the interruption. I need the following students to come to the main office at this time. Destiny Fanny, Emily Stubblefield, Abigail Harold, Zelia Elkin, Kylie Vale, and Jacqueline Hernandez. Please come to the main office.
So we know the square root of 16 is 4. In other words, something times something has to equal 16. It has to be the same thing, right? And if I multiply a positive 4 times a positive 4, I get 16. I know that, right? And if I multiply a negative 4 times a negative 4, I get 16 as well. Is there any way that I can multiply the same number times the same number and get a negative answer? What do you think? Octavian, is there any way I can get a negative times a negative? Excuse me, it's got to be two different numbers. It can't be, it's got to be negative times a positive. So is there any way that I can get a negative answer and it be the same thing times the same thing? Yeah, when you multiply. Well, that doesn't change when I multiply. Remember, in order to get a positive answer, I have to multiply a positive times positive or a negative times a negative, right? But there's no way I can multiply the same thing times the same thing and get a negative answer. The only way when I multiply and get a negative answer is to multiply a positive times a negative, right? So it's impossible to have the square root of a negative 16. Because the only way I get 16 is to multiply positive 4 times positive 4 or negative 4 times negative 4. But in order to get negative, one has to be positive, it has to be negative. So any negative number, you might want to write that down. Any negative under square root will be an imaginary number. And like I said, you're not going to deal with those in Algebra 1, but you will see those in Algebra 2. All right, so let's look at one other slide that's really important here. You really will want to come back to this slide. You'll really want to maybe even download it on your computer or something, because this is one of the best explanations of classifying numbers you'll ever find. What if I asked you to classify the number 3? Here it is. It's a natural number, right? But if it's in the innermost box, it's also included in all the boxes. Okay? So the natural number 3 is also a whole number. It's also an integer. It's also a rational. And it's also a real. What if I asked, what is negative 3? Well, you said, well, negative 3, it's not a whole number because it's not in that box. It's not a whole, and it's not in the natural number. Negative 3 is an integer, but it's also a rational number, and it's a real number. What if you asked about a repeating 1? Well, it's a rational number, and it's a real number. If you asked about pi, pi is an irrational number, but it's also a real number. When we classify numbers, we're going to have at least 2 different classifications for every number except imaginary. All right? Questions on that? Here's what I'd like to do. I may have already sent it to you. Let me look right quick. At the top of your classwork, you're going to see a slide that says classifying numbers. I want you to open that, click on it. And it's a Desmos activity, okay? So go there, please. We're going to do that together for just a minute or two. So everybody log on right quick. In fact, I'm going to put you on the second slide. See if everybody's logged on. Looks like about everybody's there. Octavian, yeah, you're with us now. Awesome. All right, so here's the deal. Let's look at that right quick. The number 11, is it a natural number? Yes or no? Oh, yeah. So if it's a natural number, automatically, remember the boxes? It's a whole number, it's an integer, it's a rational number, and it's a real. Okay? It wouldn't be an irrational number, it wouldn't be imaginary, but it's going to be all the others. It's a whole number, yeah. It's an integer, yeah. It's a rational number. You know, and if we start with natural number, we're going to include all these down to real except for rational and imaginary. So mark yours, please. Look at number 3. Ooh, square root of 3. Okay? It's got a square root, so there is no perfect square root of 3, is there? All right, so it's irrational. And it's also, if it's irrational, it's also real because remember, rational and irrationals are both real numbers. The only thing that's not real is imaginary, like Mickey Mouse. So go ahead and mark yours, please. You should have marked rational and real. -7. Is -7 a natural number? No, it's got a negative. Is -7 a whole number? No, it's negative, isn't it? Is it an integer? Yeah, so mark integer, which means if it's an integer, it's rational and it's real. Check out the next one. Five over 2. Well, that's not a natural number, is it? Is it a whole number? No, it's a fraction. It's a fraction. It's not, and it doesn't divide out evenly. Then it's not an integer. So it's a rational number, and it's a what? Real. Yes. Okay, let me give you about 3 minutes to try 6, 7, and 8 on your own. Okay. Yes, sir. Can you wait about 3 minutes here and then go? Yeah, let's knock these last 4 problems out, and you're good to go. We look at 0. Is it a natural number? No, but it is a whole number, integer, rational, and real. Kevin, can I ask you a question? So what is this one? The square root of -9? Yes, sir. It's imaginary, and it's not anything else. If you missed that one, go back and fix it. It's just imaginary. That's it. Why is it imaginary, Kevin? Perfect, because it's a negative square root. Awesome. Madison, can I ask you a question? All right. So looking at pi, what is it? It's irrational. Here's a place a lot of you will want to make a mistake if you're not careful. It's irrational and real. Perfect. Last one, and this one's going to be a little bit tricky. I want to be sure we get this right. 8 divided by 4 is what? What? 2. And this is a negative number because there's a negative sign sitting out front. So instead of this being 8/4, it's actually -2. So what's -2? Is it an integer? Yes. Is it? If it's an integer, it's not a whole number, is it? No, it's not a natural number either. So that means it's an integer, it's a rational, and it's real. You've got to mark those 3 for this answer to be correct. All right, so now you can identify and classify numbers.